Architecting for Agility, a practical guide to CQRS and strategic system design. The evolving landscape of software architecture. In the digital age, software has become the invisible backbone of our daily lives, orchestrating everything from our morning coffee order to global financial transactions. Businesses, large and small, now fundamentally rely on software to operate, innovate, and compete. Yet, as our reliance on technology grows, so does the complexity of the systems we build. The demands placed on modern applications to be faster, more scalable, more resilient, and simpler to maintain are pushing the boundaries of traditional architectural models. From a user's perspective, software ideally functions seamlessly. You tap a button and something happens instantly. You search for information and it appears. But behind that smooth facade often lies an intricate web of code, databases, and network communications, painstakingly designed to meet these burgeoning demands. Why traditional architectures sometimes fall short. For many years, the monolithic architecture was the standard. Imagine a single, large application built as a single, indivisible unit. All the business logic, the user interface, and the data access layers are bundled together. This approach has its merits, especially for smaller projects or startups, as it's often simpler to develop initially, deploy, and manage. A single code base means easier debugging, and all components communicate directly in memory, leading to fast interactions. However, as applications grow in complexity and scale, the monolith starts to show cracks. Scalability challenges. If one part of the application becomes a bottleneck, e.g., intensive reporting features, the entire application must be scaled, even parts that don't need the extra resources. This can be inefficient and costly. Maintenance headaches and developer nightmares. A large, tightly coupled code base can become incredibly difficult to understand, modify, and test. A change in one area might inadvertently break another, leading to increased risk, slower development cycles, and fear of change among teams. Technology lock-in. The entire system is often built using a single technology stack. Introducing new technologies or upgrading existing ones can be a monumental task, potentially requiring a complete rewrite. Deployment bottlenecks. Even a tiny change requires redeploying the entire application, which can lead to longer downtime windows and complicated rollback procedures. Team friction. Large teams working on a single code base can step on each other's toes, making collaboration challenging and slowing down progress. Beyond the monolith, many applications also adopted the CRUD, create, read, update, delete, model as a guiding principle for interacting with data. In a typical CRUD application, a single data model, often represented by tables in a relational database, serves as the source of truth for both capturing new information and retrieving existing data. When you add a new customer, you create a record. When you view customer details, you read the record. When a customer updates their address, you update it. When a customer leaves, you delete their record. This model is intuitive and powerful for many typical business operations. For simple applications, where the way data is stored is largely the same as the way it's read and updated, CRUD works perfectly. But its simplicity can mask underlying complexities when faced with diverging requirements. Conflicting optimizations. The data model that's best for ensuring transactional integrity during a create or update operation, e.g., highly normalized tables to prevent data duplication, might be highly inefficient for a complex read operation, e.g., needing to join many tables to generate a report or display a detailed dashboard. Security granularity. Applying distinct security rules for different types of operations can become cumbersome. Performance bottlenecks. A single data store or model might struggle to handle high volumes of both write operations and read queries simultaneously, especially if they have different performance profiles. For instance, a system might need to process thousands of orders per second writes, while also needing to display complex, real-time sales analytics dashboards, reads, efficiently. The growing need for specialized architectural patterns. As a direct response to these limitations, and driven by increasingly complex business demands, the software industry began searching for more specialized architectural patterns. The goal was to build systems that could scale independently, allow different parts of an application to scale up or down based on their individual load, rather than forcing the entire system to follow. Optimize for diverse demands. Cater to wildly different needs for writes, e.g., consistency, transactional integrity versus reads, e.g., speed, flexibility, specific data structures. Enhance modularity. Break down systems into smaller, more manageable, and independently deployable components, fostering agility and resilience. Improve maintainability. Make it easier for development teams to understand, modify, and extend specific parts of the system without impacting others. Accommodate technological diversity. Enable the use of the best tool for the job, allowing different components to leverage different databases or technologies where appropriate. This shift in thinking led to the rise of concepts like microservices, where an application is composed of many loosely coupled, independently deployable services. Each service owns its data and its specific business capabilities. While microservices address many drawbacks of monoliths, they also introduce new complexities, particularly around data consistency and communication between services. A brief primer on domain-driven design, DDD, as a foundational concept. Before diving deeper into specialized patterns, it's crucial to understand a foundational concept that underpins many modern architectural approaches, including CQRS, domain-driven design, DDD. Coined by Eric Evans in his seminal 2003 book, Domain-Driven Design, Tackling Complexity in the Heart of Software, DDD isn't a technology or a specific architectural pattern itself. Instead, it's an approach to software development for complex systems that places the domain model at its core. The domain refers to the problem space your software is trying to solve, e.g., for an e-commerce company, the domain includes concepts like orders, products, customers, payments, shipping. The domain model is a representation of the business concepts, their relationships, and the rules governing them. Key ideas from DDD that are particularly relevant: ubiquitous language, establishing a common vocabulary between domain experts, business users, and developers to ensure everyone is on the same page. This language is then used in the code itself. For example, if the business talks about placing an order, the code should have place order commands and related entities. Bounded contexts, recognizing that terms can have different meanings in different parts of a large system. For instance, a product in a sales context might have a price and a description, but in a manufacturing context, it might have production dates and materials. A bounded context defines a logical boundary within which a specific domain model is consistent and makes sense. It helps manage complexity by breaking a large domain into smaller, cohesive pieces. Aggregates. Within a bounded context, an aggregate is a cluster of associated domain objects, entities, and value objects that are treated as a single unit for data changes. It has a root entity, often called the aggregate root, which controls access to the other objects within the aggregate and ensures their consistency. For example, an order might be an aggregate root, encapsulating order items and handling their life cycle. All changes to an order's items must go through the order aggregate root to ensure business rules are enforced. DDD encourages developers to deeply understand the business domain, model its complexity, and build software that directly reflects that understanding. It provides a structured way to manage the inherent complexity of enterprise systems, laying the groundwork for how various architectural patterns like CQRS can fit together. In the next chapter, we will delve into the core dilemma that specifically led to the emergence of CQRS, highlighting how the single model approach began to buckle under the strain of conflicting operational requirements. Understanding the problem, why CQRS emerged. To truly appreciate the power and purpose of Command Query Responsibility Segregation, CQRS, we must first understand the fundamental problem it seeks to address. As highlighted in the previous chapter, traditional software architectures, particularly those built around a single, unified data model, often CRUD-centric, begin to strain under certain conditions. This strain isn't just about technical performance. It's about the conceptual friction that arises when you ask one model to fulfill two fundamentally different, often conflicting, purposes. The single model dilemma. When one data model for reads and writes becomes a bottleneck, imagine a busy restaurant. In a traditional setup, the waiters take orders, send them to a single kitchen staff member who prepares the food, and also answer all customer questions about the menu, ingredients, and waiting times. This single person serves as both the order processor, write operations, and the information provider, read operations. When the restaurant is small, this works fine. But as it grows and more customers arrive, this single person becomes a bottleneck. The wait staff slows down because their questions about menu items disrupt the cooking process. The cooking process is interrupted because questions need immediate answers. The single individual optimized for one task, cooking, is now burdened by another, information retrieval, and neither task gets done as efficiently as it could. This analogy directly applies to software systems. In many applications, particularly those following a strict CRUD pattern, the same data model and often the same codebase are used for writing data, handling new information, updating existing records, and enforcing business rules, e.g., placing an order, updating a user's profile, debiting an account. This requires strong consistency, transactional integrity, and often complex validation logic. Reading data, retrieving information for display, reporting, or analysis, e.g., showing a user's order history, displaying product catalogs, generating daily sales reports. This often prioritizes speed, flexibility in query structures, and the ability to serve up data in various formats optimized for presentation. The dilemma arises because the optimal design for these two operations often diverges significantly. Right-side optimization typically focuses on normalization, reducing data redundancy to ensure data integrity and make updates more efficient. Transactional consistency, ensuring that complex operations either complete entirely or are fully rolled back. Validation, applying strict business rules before accepting data. Red-side optimization typically focuses on denormalization, duplicating or pre-calculating data to speed up queries, often by eliminating the need for complex joins. Performance, fast retrieval, minimal latency, optimizing for specific UI layouts or reporting needs. Flexibility, easily adapting to new query parameters or display requirements. Trying to force both highly divergent requirements onto a single, unified data model inevitably leads to compromises. The model becomes either too complex for writes, too slow for reads, or both. This one-size-fits-all approach ends up fitting none of the sizes particularly well, leading to architectural friction and performance bottlenecks. Conflicting requirements, high-volume transactions versus complex reporting. Let's consider a practical example, an online ticketing system. Scenario 1, high-volume transactions, writes. When a popular concert goes on sale, thousands, even millions, of users simultaneously attempt to buy tickets. This is a classic high-volume write operation. The system needs to process ticket purchases rapidly. Ensure atomicity. A ticket sale must either fully succeed, deduct money, assign seat, confirm order, or fully fail. Maintain strict consistency. No overselling of seats, no double booking. Handle concurrency. Multiple users trying to buy the same seat simultaneously must be managed safely. Enforce business rules. Limited number of tickets per customer, valid payment, etc. For these requirements, a highly normalized database with strong transactional guarantees, like a traditional relational database, is often ideal. Scenario 2. Complex reporting and analytics, reads. Meanwhile, the concert promoter and various stakeholders need to know how many tickets were sold for each pricing tier, what percentage of tickets were sold via mobile versus desktop, which geographical regions are generating the most sales, what's the average purchase price, how does this concert sales trend compare to similar events last year, display real-time seat availability maps. These are complex read operations. They often involve aggregating vast amounts of data, performing complex calculations, and displaying results quickly, sometimes visually. A normalized transactional database, while excellent for writes, might be incredibly slow for these types of analytical queries, which would necessitate numerous joins across large tables or require scanning millions of records. building a user interface on top of such queries would lead to a sluggish experience. If both of these operations hit the same database and the same data model, one will inevitably suffer. If you optimize the database for fast writes, complex reads will be slow. If you denormalize the database for fast reads, writes become more complicated, as you have to update multiple locations, and transactional consistency becomes harder to maintain. This fundamental conflict is a common pain point in many enterprise applications. The conceptual divide: actions, changing state, versus insights, retrieving state. The core of the problem often boils down to a fundamental conceptual divide. Actions, commands, these are about doing something. They express intent and lead to a change in the system's state. When you tell a system to process payment or cancel subscription, you're giving it an instruction to modify its internal state. These operations are inherently imperative and transactional. Insights, queries, these are about knowing something. They ask for information about the current state of the system without affecting it. When you ask, "What's my current balance?" or "Show me all pending orders," you're seeking information. These operations are inherently declarative and read-only. In our daily lives, we intuitively separate these. When you tell your smart speaker, "Turn off the lights," that's an action. When you ask, "What's the weather like?" that's a query. You don't expect asking about the weather to suddenly dim your lights, nor does telling it to turn off the lights require it to then recite the weather back to you. The responsibilities are distinct. Yet, in many software systems, we blur this line. We create general-purpose services or repositories that can both modify and retrieve data using the same underlying models and methods. While convenient for simple operations, this intertwining of responsibilities becomes problematic as systems grow. It obscures the true intent of operations. It complicates security, as read and write permissions are often bundled. It makes it harder to optimize for performance, as you're trying to satisfy two different goals with one solution. It increases the risk of side effects, where a read operation might accidentally or intentionally, but confusingly, trigger a state change. Setting the stage for a different approach. Recognizing this fundamental conceptual and technical conflict is the first step towards understanding why CQRS emerged. It's not merely an optimization technique. It's a paradigm shift in how we think about the flow of data and the responsibilities within a system. Instead of trying to force a single model to do everything, CQRS proposes a targeted separation of concerns, allowing each side of the equation, writes and reads, to be optimized independently using the best techniques and tools available for their specific purpose. This strategic divergence tackles the inherent tension between changing data and retrieving data, paving the way for more scalable, performant, and maintainable systems in complex domains. The next chapter will introduce the core principles of CQRS and illustrate how this separation works in practice. Introducing CQRS, separating commands from queries. Having established the fundamental problem of conflicting requirements for writes and reads, we can now introduce the solution proposed by Command Query Responsibility Segregation, or CQRS. At its heart, CQRS is a pattern that radically separates the operations of telling a system to change something from the operations of asking a system for information. It's a powerful idea that, once understood, can profoundly change how you design complex software. The core principle of Command Query Responsibility Segregation. The term Command Query Responsibility Segregation might sound technical and intimidating, but its meaning is quite literal. Command, an instruction to the system to do something or change its state. Query, a request to the system to give information about its current state. Responsibility segregation, keeping these two responsibilities distinct and handled by different parts of the system, potentially using different models and even different underlying data stores. Think back to our restaurant analogy. Instead of one person doing everything, imagine a clear division of labor. The kitchen staff writes, solely focused on preparing orders. They receive detailed instructions, commands from the waitstaff, confirm they are received, and execute them. They don't handle customer inquiries. Their goal is efficient, accurate food preparation. The front-of-house staff reads, solely focused on interacting with customers. They take orders, passing them as commands to the kitchen, answer questions about the menu, wait times, or special offers, queries. They manage the customer experience and retrieve information from a system optimized for quick answers, perhaps a screen displaying order statuses or a menu board. This separation means that the kitchen can be optimized for processing orders quickly and consistently, perhaps with specialized equipment and refined processes. The front of house can be optimized for customer interaction, with systems that display information rapidly and clearly. Neither interferes with the other. In the context of software, CQRS advocates for treating these two types of operations, commands and queries, as fundamentally different, each with its own design considerations and implementation pathways. Simple analogies to demystify the separation. Let's use a couple more analogies to solidify this concept, ensuring it's clear for anyone, regardless of their technical background. Analogy 1, a bank account. Command, debit my account for $50. This is an instruction to change the state, reduce your balance. You expect the change to happen accurately and reliably. You don't necessarily need to know how much money is left immediately after the debit, just that it happened. Query, what is my current account balance? This is a request for information. It should return your balance quickly, and it doesn't change your account in any way. In a CQRS system, the logic for processing the debit command would be separate from the logic for answering the current balance query. They might even look at different representations of your account data. For instance, the debit system might be heavily optimized for transaction processing and audit trails, while the balance query system might reference a pre-calculated, rapidly accessible snapshot of balances designed for quick display. Analogy 2, a to-do list application. Command, add buy groceries to my to-do list. This changes the list. Command, mark do laundry as complete. This changes the status of an item. Query, show me all incomplete tasks. This retrieves a list. Query, what are my tasks due tomorrow? This retrieves a filtered list. Without CQRS, a task service might have methods like add task, mark as complete, get all tasks, get tasks due tomorrow. While seemingly simple, this service is responsible for both changing and retrieving data. With CQRS, these responsibilities are distinctly separated into commands and queries, handled by different components. High-level overview of commands, queries, and their handlers. Breaking down the core components, a CQRS system typically involves commands, what they are, simple, intention-revealing messages that encapsulate an action to be performed. They describe what should happen, not how. They are typically named in the imperative mood, e.g., place order, change address, deactivate user. Characteristics, immutable. Once created, a command object should not be changed. Serializable, they often need to travel across process boundaries, e.g., from a web application to a backend service, so they must be easily converted to and from data formats. Single responsibility. Each command should ideally represent a single, atomic business action. No return values typically. A command handler usually doesn't return data directly, other than perhaps a confirmation of receipt or an error status. The effect of the command, the state change, is observed later through a query. Command handlers. What they are, dedicated classes or functions responsible for executing a specific type of command. There is typically a one-to-one relationship between a command and its handler. Responsibilities, receive the command. Perform validation, e.g., is this user authorized to place this order? Is the product in stock? Load the necessary aggregate, a concept from domain-driven design we briefly touched upon, representing a consistency boundary from the right-side data store. Execute the business logic within the aggregate, which changes its state. Persist the state change back to the right-side data store. Potentially publish events that describe what just happened, e.g., order placed event, user activated event, which will be crucial for updating read models. Queries. What they are, messages or function calls that represent a request for data. They are typically named in a descriptive way, e.g., get user profile query, get product catalog query, get order history query. Characteristics. Immutable, they are read-only requests. Serializable, similar to commands, they may travel across processes. No side effects, Executing a query should never change the state of the system. Return values. Queries always return data. Query handlers. What they are: dedicated classes or functions responsible for retrieving data to fulfill a specific query. Responsibilities. Receive the query. Access the appropriate read model, a concept we'll explore in detail in Chapter 5 and 6, a data structure specifically optimized for this query. Retrieve the data from the red-side data store. Return the data to the caller. They are typically much simpler than command handlers, as they only focus on data retrieval and aggregation, not complex business logic or transactional consistency. Initial benefits of clearer intent and simplified responsibilities. Even at this high-level overview, some immediate benefits of CQRS start to emerge. Clarity of intent. Every piece of code is clearly either about changing state, a command and its handler, or retrieving state, a query and its handler. This makes the codebase much easier to understand and navigate. You instantly know the purpose of any given component. Simplified design. By separating concerns, each component can be designed and optimized for its specific responsibility. Command handlers can focus solely on enforcing business rules and transactional integrity without worrying about how data will be displayed. Query handlers can focus solely on efficient data retrieval without worrying about data validation or complex state changes. Reduced complexity. While introducing more components, it simplifies the individual components. A class doesn't try to be a jack of all trades. It has one job and does it well. This makes testing, debugging, and maintaining individual parts of the system simpler. Foundation for independent scaling. Because the paths for writes and reads are distinct, you can imagine scaling them independently. If your application has a high volume of reads but fewer writes, you can add more resources to the read side without unnecessarily burdening the write side, leading to more efficient resource utilization. CQRS is not just about performance. It's about architectural clarity and enabling flexibility in systems that face diverse and often conflicting demands. It lays the groundwork for more advanced optimizations and capabilities, which we will explore in subsequent chapters. Next, we'll dive deeper into the world of commands, their structure, behavior, and the critical role of their handlers. Deep dive into commands, intent, and execution. In the CQRS pattern, commands are the driving force behind all state changes in our system. They represent the actions initiated by users or other systems, clearly articulating an intent to modify the application's data. Understanding their nature, structure, and how they are handled is paramount to grasping the right side of a CQRS architecture. What exactly is a command? Characteristics, structure, and immutability. A command is essentially an instruction to the system to do something. It's a declarative statement of intent. For example, instead of a generic update product method that takes many parameters, a command would be specific: change product price, add product to stock, or deactivate product. This shift in naming reveals a powerful concept. Commands are rich in meaning, directly reflecting the business operations they encapsulate. Let's break down the typical characteristics of a command. Intent-revealing name. As mentioned, command names are verbs, often in the imperative form, followed by the noun they act upon. Examples: place order, register user, update shipping address, process payment. This makes the code self-documenting and easier to understand for anyone familiar with the business domain. DTO, data transfer object nature. A command is usually a simple data structure. It contains all the necessary data to perform the requested action, but no behavior or logic of its own. It's a pure data carrier. For place order, it might include customer ID, product ID list, quantities, shipping address. For change product price, it would typically contain product ID and new price. Immutability. Once a command object is created and populated with data, its state should not change. This ensures that the instruction remains consistent from its creation until its execution. Immutability also simplifies reasoning about concurrency and data integrity, especially in distributed systems. Serialization friendliness. Commands often need to be passed around the system, sometimes across network boundaries, e.g., from a web frontend to a backend service or between microservices. Therefore, they must be easily serializable into formats like JSON or protocol buffers. Uniqueness, optional but recommended. While not strictly required for every command, sometimes a command will carry a unique identifier, e.g., a GUID or UUID. This is particularly useful for idempotency, ensuring that if a command is accidentally sent multiple times, it only produces its intended effect once. It also aids in tracking and debugging. No return values. Ideally, a command does not return data. Its primary purpose is to change state. Success or failure is typically communicated through exceptions, status codes, or by publishing events, which we'll discuss later. If an operation needs to return data, it's typically an indication that a query is also involved, or that the design might need refinement. Example command structure, conceptual. Command to register a new user. Class register command. Public read-only userid. String public read-only username. String public read-only email. String public read-only password hash. String. Or a secure token for password reset. Public read-only registration date. Date, constructor user ID. String username. String email. String password hash. String. This .userid equals userid. This .username username. This email equals email. This password hash equals password hash. This registration date equals new date. Notice how all properties are read-only to enforce immutability. Each property is directly relevant to registering a user. The role of command handlers, orchestrating business logic, validation, and persistence. Commands themselves are inert. They are merely the instructions. The actual work is performed by command handlers. A command handler is a specific piece of code designed to execute one and only one type of command. This one-to-one mapping, one command type to one command handler type, is a fundamental principle in CQRS. The command handler acts as an orchestrator, coordinating the various steps required to fulfill the command's intent. Its responsibilities typically include receiving the command. The handler is invoked when a specific command arrives in the system. This often happens via a dispatcher mechanism that routes commands to their appropriate handlers. Command validation. The handler first verifies if the command itself is valid. This isn't about business rules yet, but rather about the command's structure and completeness. For example, does register user command have a non-empty username and a valid email format? This is often called command validation or syntactic validation. Loading the state aggregate. If the command modifies an existing entity, the handler is responsible for retrieving the current state of that entity, or more specifically, its domain-driven design aggregate from the database. For example, an update shipping address command handler would load the customer aggregate. Executing business logic and state change. This is the core responsibility. The handler invokes methods on the loaded aggregate, or creates a new one if it's a creation command, that embody the business rules the command needs to execute. The aggregate performs the actual state change. Crucial point. The business logic should reside within the domain model, e.g., within the customer class method change address, not directly inside the command handler. The handler merely orchestrates the call to the domain. This ensures that business invariants are maintained within the domain itself. Persistence. After the business logic has been applied and the state of the aggregate has been updated in memory, the handler is responsible for persisting these changes back to the database. This typically involves saving the modified aggregate. Publishing domain events, optional but recommended. A very powerful practice, especially when combining CQRS with event sourcing, which we'll discuss in detail in Chapter 7. After successfully processing a command and persisting the state change, the command handler often publishes one or more domain events. These events describe what has happened, e.g., order placed event, shipping address updated event, user registered event. These events are crucial for communicating changes to other parts of the system, particularly the read side to enable updating read models. Example command handler, conceptual. Handler for the register user command. Class register user command handler. Private read-only user repository, iUser repository. Interface for data access. Constructor, user repository, iUser repository. This .user repository equals user repository. Public async handle command, register user command, promise evade. 1. Command validation, e.g., using a library or manual checks. If command.username, command.username length 3. Throw new invalid command exception. Username is too short. If is valid email, command email. Throw new invalid command exception. Invalid email format. 2. Business rule validation, e.g., username uniqueness. Const existing user equals await this .user, repository find by username, command.username. If existing user, throw new business rule violation exception, username already taken. 3. Create or load aggregate, in this case, create a new user aggregate. Const new user equals user register, command.userid, command.username, command email, command password hash. 4. Persistence. Await this .user repository save, new user. 5. Publish domain event, e.g., for email confirmation, red model updates. Await event publisher publish, new user registered event, new user ID, new user email. Notice how the handle method is concise. It delegates the actual user registration, logic user register, to the user domain entity itself, ensuring that user maintains its own invariants, ensuring atomicity and transactional integrity on the right side. A cornerstone of the command handler's responsibility is guaranteeing atomicity and transactional integrity. When a command is processed, all the changes resulting from it must succeed or fail as a single, indivisible unit. If any part of the operation fails, the entire transaction should be rolled back, leaving the system in its prior consistent state. In many systems, this is handled by database transactions. The command handler will typically begin a database transaction, perform all necessary reads, loading the aggregate, and writes, saving the modified aggregate. If all operations succeed, commit the transaction. If any operation fails, roll back the transaction, undoing all changes made within that transaction boundary. This ensures that the business rules are applied consistently and that the right-side data remains coherent. This focus on transactional consistency on the right side is paramount, protecting the fundamental integrity of your system's state. The power of clear, intention-revealing command names. This might seem like a minor point, but naming conventions in programming have a profound impact on readability, maintainability, and collaboration. In CQRS, the imperative nature of command names is incredibly powerful. Self-documentation. A file called placeOrderCommandCS or placeOrderCommandHandlerJava immediately tells any developer what this code does. There's no ambiguity. Reduced cognitive load. When reviewing code or debugging, you don't need to guess the purpose of a generic process data method. A cancel subscription command explicitly states its intent. Enforced granularity. The act of naming a command forces you to think about the single business action it represents. If a command name becomes too generic or combines multiple unrelated actions, e.g., manage customer details, it's a clear signal that it should be broken down into more specific commands, e.g., update customer address, change customer email, deactivate customer account. This leads to a cleaner, more modular design. Clear API. From a public API perspective, commands present a clear, verb-driven interface to your system, making it easier for client applications to understand how to interact with it. Commands are the lifeblood of the right side in CQRS. They encapsulate the intention to change state, and their dedicated handlers ensure that these changes are performed with precision, integrity, and adherence to business rules, forming a robust foundation for your system's transactional capabilities. Now that we've explored how state is changed, the next chapter will shift our focus to how that state is efficiently retrieved through queries. Exploring queries, efficient data retrieval. In a CQRS architecture, if commands are about bringing about change, then queries are about gaining insight. After meticulously defining how state is manipulated and consistently updated on the right side, we now turn our attention to the read side. How do we efficiently retrieve data to satisfy diverse user needs and application requirements? This is where queries and the concept of read models come into play. What exactly is a query? Characteristics, structure, and idempotency. A query is a request for data, pure and simple. Unlike commands, queries are passive. They do not and must not alter the state of the system. Their sole purpose is to retrieve information for consumption, whether that's displaying data to a user, generating a report, or feeding another system. Let's look at the key characteristics of a query. Read-only nature. This is the most crucial characteristic. A query's execution should have no side effects on the system's state. It's like asking a question. The act of asking a question doesn't change the answer itself. DTO, Data Transfer Object, nature. Similar to commands, queries are typically simple data structures that encapsulate the parameters needed to retrieve the desired data. They don't contain business logic. For getProductDetails query, it might only include producted. For listActiveUsers query, it might contain page number, page size, and sort by field. Return values. Queries always return data. The type of data depends entirely on the query's purpose. It could be a single object, a collection of objects, a paginated list, or a complex report. Idempotency. Executing the same query multiple times with the same parameters should yield the same results, assuming the underlying data hasn't changed. This is inherently true for read-only operations, reinforcing their safe nature. Serialization friendliness. Like commands, queries often traverse network boundaries, so they must be easily serializable. Descriptive naming. Query names are typically nouns or phrases that describe the data being requested, e.g., product details, customer orders, user activity log. They are explicit about what they aim to retrieve. Example: query structure, conceptual, query to get details of a specific product. Class getProductDetails query. Public read-only producted, string. Constructor product ID, string. This .producted equals producted. Query to get a paginated list of orders for a customer. Class getCustomerOrders query. Public read-only customerID, string. Public read-only page number. Number, public read-only page size. Number, constructor customer ID, string, page number, number, page size, number. This customerID equals customerID. This page number equals page number. This page size, page size. The role of query handlers. Retrieving data explicitly for display or analysis. Just as commands have command handlers, queries have query handlers. A query handler is responsible for fulfilling a specific query request. Similar to command handlers, there's usually a one-to-one mapping between a query type and its handler. The responsibilities of a query handler are typically much simpler and more focused than those of a command handler. Receiving the query, the handler is invoked when a specific query is dispatched to the system. Accessing the read model. This is the crucial step. Unlike command handlers that interact with the transactional write model, often the domain model, query handlers interact directly with a read model. A read model is a data structure or an entire database specifically optimized for the query at hand. Data retrieval. The handler executes a query, e.g., a SQL query, a NoSQL database lookup, a search index query, against the read model's data store to retrieve the requested information. This often involves transforming data into the exact shape required by the consumer, e.g., a UI component, a report generator. Returning results. The handler returns the retrieved data to the caller. Example: query handler, conceptual. Handler for getProductDetails query. Class getProductDetails query handler. Private read-only product read store, iProduct read store. Interface to read optimize store. Constructor product read store, iProduct read store. This .product read store equals product read store. Public async handle query, getProductDetails query. Promise product details DTO null. One data retrieval from read model, e.g., a denormalized view or JSON document. Const product details equals await this .product read store get by ID query.producted. 2 return results, often a DTO tailored for UI. Return product details. Handler for getCustomerOrders query. Class getCustomerOrders query handler. Private read-only, order report DB. iOrder report database. Interface to a reporting database. Constructor order report DB. iOrder report database. This order report DB equals order report DB. Public async handle query. getCustomerOrders query. Promise paginated orders DTO. Retrieve orders optimized for display, perhaps already joined and paginated. Const orders equals await this order report db get customer orders. Query customer id. Query page number. Query page size. Const total equals await this order report db get customer order count. Query customer ID. Return orders total. Notice the directness. The query handler simply fetches data. There's no business logic, no validations, no state changes executed within the handler. It's a pure data conduit, introducing read models, projections, tailored data structures optimized for specific query needs. The secret sauce of the CQRS read side is the read model, also frequently referred to as a projection. A read model is a specifically crafted representation of the data, optimized solely for reading and fulfilling specific query requirements. Why are read models so important? Decoupling. They decouple the read requirements from the write data model. This means you can evolve your reading needs, e.g., new reports, richer UI displays, independently of your core transactional write model. Performance optimization. Read models are designed for speed. They often involve denormalization, flattening relationships and pre-joining data so that a single query can retrieve all necessary information without complex database joins. For example, a product details read model might include the product name, description, category name, and average customer rating, even if these pieces of information reside in different tables in the write model. Data aggregation, pre-calculating sums, averages, or counts. A sales summary read model might store daily, weekly, or monthly sales totals, eliminating the need to calculate them on the fly for every report. Specialized storage, using different types of databases or data stores that are best suited for the specific query patterns. For example, a search engine like Elasticsearch for full-text search queries, a graph database for relationship queries, or a time series database for historical data. Tailored for UI reporting. A read model structure can directly mirror the data needed by a particular user interface screen or report. This eliminates the need for complex object relational mapping, ORM, work, or significant data transformation in the application layer after retrieval. The data arrives in the exact shape it's needed. Consider an e-commerce product example. Write model relational database. Products table, ID, name, description, weight. Categories table, ID name. Reviews table, ID, producted, customer id, rating, comment. Suppliers table, ID, name, contact info. Retrieving all data for a single product page would require multiple joins. Read model 1, e.g., a document in NoSQL, product details view for product page display. Producted, XYZ. Product name, advanced widget. Description, high performance widget for advanced users. Category, id, cat001, name, electronics. Supplier name, Global Parts Co. Average rating, 4.5. Review count, 128. Pricing, currency, USD price, 99.99, currency, EUR price, 85.00. This single document contains all necessary information for a product detail page, making retrieval extremely fast. Read model 2, e.g., indexed fields in Elasticsearch, product search index for quick search and filtering. Producted, XYZ. Product name, advanced widget. Category name, electronics. Tags, widget, advanced electronics performance. Price, 99.99. Is in stock, true. Optimized for keyword search and filtering by price, category, etc. Read model 3, e.g., a materialized view in a SQL database. Daily sales summary for reporting. Date, producted, product name, quantity sold, revenue. 2023 to 10 to 26. XYZ 123. Advanced widget 5049 99.50. Pre-aggregated data for analytical reports. Strategies for designing effective read models. Designing effective read models involves considering usage patterns. What specific queries will this read model serve? How often will it be queried? What information is needed together? Data structure. What is the ideal shape of the data for this query? Should it be denormalized, aggregated? What specific fields are required? Data store. What type of database or data store is best suited for this particular read model and its query patterns? Relational databases, SQL for structured queries and relationships. Document databases, MongoDB, Cosmos DB for flexible, denormalized data. Search engines, Elasticsearch for full-text search and complex filtering. Key value stores, Redis for caching and fast lookups. Graph databases, Neo4j for highly connected data. Time series databases for event logging and analytics. Consistency requirements. How fresh does the data need to be? For a critical financial balance, it might need to be very fresh. For a product catalog, a few minutes of latency might be acceptable. This informs how often and how quickly the read model is updated from the write side. This leads directly to the concept of eventual consistency, which we'll explore in the next chapter. By carefully designing queries and their corresponding read models, we can unlock tremendous performance, flexibility, and scalability on the read side of our applications, perfectly complementing the robust transactional consistency provided by the command side. The separation allows each part to excel at its designated role. The role of data models and storage in CQRS. The separation of commands and queries in CQRS inevitably leads to a fundamental architectural decision. How do we store and manage the data for each side? This chapter delves into the exciting possibilities and inherent challenges of embracing different data models and even different storage technologies for your write and read responsibilities, particularly the critical concept of eventual consistency. Embracing different data models for the write side, transactional and read side, query optimized. One of the most liberating aspects of CQRS is the freedom to use different data models on the write side and the read side. This freedom allows each side to be optimized for its primary purpose without compromising the other. The write model, optimized for consistency and integrity. The write side data model, often referred to as the conceptual model or domain model, is geared towards encapsulating business rules, enforcing invariance, and ensuring transactional integrity. Its design prioritizes normalization. Typically, this means a highly normalized relational database schema or a well-structured set of aggregates in a NoSQL store if using event sourcing. Normalization minimizes data redundancy, reducing the risk of inconsistencies during updates and making data modifications efficient. Transactional guarantees ensures that complex operations, e.g., placing an order that involves deducting inventory, creating an order record, and updating customer loyalty points, either fully succeed or fully fail. This is crucial for maintaining the single source of truth about the system's current state. Business logic enforcement. The write model is where the core business rules live, often enforced through domain entities and aggregates, as discussed in Chapter 4. For example, in an e-commerce system, the write side might use a traditional SQL database with separate tables for customers, orders, order items, products, inventory, etc., with foreign key constraints and ACID transactions to guarantee data integrity. The read models, optimized for performance and query flexibility. In stark contrast, the read models are designed purely for efficient data retrieval. Their design prioritizes denormalization. Data is often duplicated and structured to match the exact requirements of specific queries or UI screens. This eliminates the need for complex joins and calculations at query time, drastically improving performance. Aggregation. Data is often pre-aggregated or pre-calculated to serve reports or dashboards directly. Presentation-oriented. The structure of a read model might closely resemble the JSON structure expected by a front-end application or the columnar structure needed for a BI tool. High read throughput. Designed to handle many concurrent read requests with low latency. Using our e-commerce example, while the write side has separate tables, a read model for a product details page might combine product information, average ratings, and available stock into a single JSON document in a NoSQL database. Another read model for customer order history might be a denormalized table or view that already includes customer names, product titles, and total prices, optimized for a paginated list view. The possibility and benefits of using different storage technologies. The logical separation of data models naturally extends to the physical separation of storage technologies. This is where CQRS truly leverages the best tool for the job philosophy, often leading to a polyglot persistence strategy. You could use right-side storage, relational databases, SQL, PostgreSQL, MySQL, SQL Server, Oracle excellent for transactional integrity, complex joins when reading from the right model, which is rare for end users, and robust consistency. Event stores. For event sourcing, which we'll cover in Chapter 7, a specialized database optimized for storing immutable sequences of events, e.g., EventStoreDB, Kafka as an event log. Read-side storage. Document databases, NoSQL, MongoDB, Couchbase, Azure Cosmos DB ideal for flexible schemas, denormalized data, and easy mapping to UI components. Key value stores. Redis Memcached excellent for caching frequently accessed data or simple lookups. Search engines. Elasticsearch, Apache Solr perfect for full-text search, faceted navigation, and complex filtering. Graph databases. Neo4j, Amazon Neptune, when relationships between data points are paramount, e.g., social networks recommendation engines. Columnar databases. Apache Cassandra, Apache HBase for analytical workloads or large-scale aggregate reporting. Traditional relational databases. Even a different instance or schema of a SQL database can serve as a read model, perhaps with materialized views or heavily denormalized tables. Benefits of polyglot persistence. Optimal performance. Each data store is chosen because it excels at its specific purpose, e.g., a search engine for searching, a document store for showing product details. Scalability. Read models can be scaled independently, often much more easily and cheaply than the transactional write model, as they frequently involve simpler data access patterns. Flexibility. Easily introduce new read models or change existing ones without impacting the write side. If a new reporting requirement emerges, you can build a new read model without migrating your core transactional data. Reduced load on write store. Offloading all read traffic from the transactional database protects its performance and ensures it's solely focused on maintaining consistency. Understanding and managing eventual consistency. What it means, why it happens, and how to embrace it. When you separate your write and read models, and especially when you use different data stores, a crucial concept emerges: eventual consistency. This is often the most challenging aspect of CQRS for developers and business stakeholders to grasp, as it represents a departure from the immediate consistency often assumed by traditional CRUD applications. What is eventual consistency? Simply put, eventual consistency means that after a successful write operation to the write model, the corresponding read models may not immediately reflect that change. There will be a propagation delay, during which the read model is stale. However, eventually, given enough time and no new updates to the data, all read models will converge and reflect the latest state from the write model. Why does it happen? The delay occurs because updates to read models are typically asynchronous. When a command is successfully processed and the write model is updated, and potentially an event is published, it takes time for the event to be published to a message broker. The read model builder, a dedicated service, often called a projector, to consume that event. The read model builder to process the event, update its specific data store, and make the change available for queries. This indirect path means that a user might commit an action, e.g., change their profile picture, and then immediately try to view it, only to see the old one for a brief period. How to embrace and manage eventual consistency. Educate stakeholders. This is paramount. Business users and product owners must understand that not all data will be instantly synchronized. Managing expectations is key. Design for lag, user interface feedback. Provide immediate feedback to the user that their action was successful, even if the subsequent read is delayed. For example, after an order is placed, show a "your order is being processed" message, or flash a confirmation, instead of immediately trying to fetch the order from the eventually consistent read model. Progress indicators. Use loading spinners or data might be slightly out of date messages. Show local data. For critical immediate feedback, e.g., a user sees their newly added item in a shopping cart, you might keep a client-side local, copy temporarily, or even issue specific queries directly against the write model for these rare, critical immediate reads, though this should be an exception. Polling WebSockets. For critical real-time updates, e.g., stock price in a trading app, the UI can poll the red model or use WebSockets to receive updates as they occur. Choose appropriate consistency levels. Not all data needs the same freshness. High consistency needed. Financial transactions, user account balances, often retrieved directly from the right model for critical consistency. Eventual consistency tolerable. Product catalog content, user profile updates, social media feeds, analytics dashboards. Monitoring and alerting. Crucially, monitor the health of your red model builders and message queues to ensure events are being processed in a timely manner. Alerts for long queues or processing delays are essential. Rebuilding read models. When you change the structure of a red model or fix a bug in a projection, you will need mechanisms to rebuild your read models from scratch, usually by replaying all historical events from the right model, especially powerful if you are using event sourcing. Mechanisms for updating read models from the right side. The bridge between the consistent right side and the fast read side is paved by mechanisms that propagate changes. The most common and robust approach involves events and messaging, domain events from right side. When a command is successfully processed and the right model state is updated, a domain event is published. A domain event describes something that happened in the domain in the past tense, e.g., order placed, customer address changed, inventory restocked. These events carry the necessary data for downstream systems to react. The right side, or its command handler, typically persists these events alongside the state change within the same transaction to guarantee atomicity. Message queues event buses. These events are then published to a reliable message queue or event bus, e.g., Kafka, RabbitMQ, Azure Service Bus, AWS SQS SNS. These systems ensure that events are delivered to interested consumers, even if consumers are temporarily offline. Read model builders, projectors, consumers. Dedicated services or components subscribe to these events. When an event arrives, the read model builder processes it, extracts the relevant information, and updates its specific read model in its designated data store. A single domain event might trigger updates to multiple read models. E.g., order placed event could update a customer orders list, a daily sales report aggregate, and a product popularity ranking. This event-driven approach provides loose coupling between the write and read sides, allowing them to evolve independently. It's a foundational component for achieving both the performance benefits of CQRS and the robustness required for modern distributed systems. The natural fit between this asynchronous, event-driven propagation and the event sourcing pattern will be the focus of our next chapter. CQRS and event sourcing. A powerful synergy. While CQRS, Command Query Responsibility Segregation, can certainly be implemented using traditional database persistence, where the right model merely saves the current state, it finds its most powerful and natural synergy when combined with event sourcing. The two patterns are distinct, but together they amplify each other's benefits, creating exceptionally robust, auditable, and flexible systems. Introduction to event sourcing. Storing all changes as a sequence of immutable domain events. Imagine a traditional database that stores the current state of an entity. If you update a customer's address, the old address is overwritten. If you place an order, the database reflects the new total and consumed inventory. You only see the now. Event sourcing takes a fundamentally different approach. Instead of merely storing the current state, event sourcing involves storing every change to an application's state as a sequence of immutable, time-ordered domain events. These events are like journal entries or a ledger, detailing every action that has ever happened in the system. The current state of an entity is then derived by replaying these events from the beginning. Consider a bank account. Traditional approach. The database holds balance $1,000. If you deposit $200, it updates to balance $1,200. The history of transactions might be in a separate table, but the core balance is a single, mutable value. Event sourcing approach. The database and event store would record account opened event balance $0. Money deposited event amount $1,000. Money deposited event amount $200. Debit card payment event amount $50. To find the current balance, you would replay these events. 0 plus 1,000 plus 250 equals $1,150. Each event is a fact that occurred in the business domain. It's immutable, meaning once recorded, it can never be changed or deleted. Common examples of events include order placed, customer address changed, invoice paid, product stock adjusted. How event sourcing naturally complements and enhances CQRS. The combination of CQRS and event sourcing is often referred to as CQRS and ease. They fit together like pieces of a puzzle. Commands generate events. In a CQRS and ease system, when a command is processed by a command handler, instead of just updating a traditional database to reflect the new state, the command handler's primary output is a new set of domain events. These events capture the facts about what just happened as a result of the command. Example: a place order command is processed. The order aggregate in memory emits an order placed event and potentially several order item added events. Events are stored, event store right side. These newly generated domain events are then appended to an event store. The event store serves as the primary persistence mechanism for the right side. It is a single, authoritative source of truth for all state changes. Because events are immutable, appending them is very fast. Events build state, read side projections. The event store also acts as a powerful source for building read models projections. As new events are committed to the event store, a messaging mechanism, often a publish-subscribe system over the event store, notifies various projectors or read model builders. These projectors consume the events and use them to update their specific read models, often stored in different, query-optimized databases. Example: order-placed event might be consumed by a customer order history projector, updating a denormalized view of past orders for the customer's dashboard. A daily sales summary projector, incrementing sales figures for a reporting dashboard. An inventory projection projector, updating available stock counts in a fast lookup store. This flow effectively separates the process of recording historical facts, event store, from the process of querying current or derived state, read models, perfectly aligning with the core tenets of CQRS. Benefits: full audit trail, time travel debugging, historical analysis, easy rebuilding of read models. Combining CQRS with event sourcing brings a host of powerful advantages. Full, immutable audit trail. Every single state change in the system is recorded as an immutable event. This provides an unparalleled level of auditability. You can always see exactly what happened, when, and why. This is invaluable for compliance, debugging, and understanding system behavior. Time travel debugging. Because you have a full history of events, you can replay the events up to any point in time to reconstruct the system's state at that moment. This is incredibly powerful for debugging complex issues or understanding how an entity arrived at a particular state. Historical analysis and business intelligence. The stream of historical events is a rich source of data for analytics. You can derive new insights by replaying events with different analytical tools or building specialized historical read models that capture trends and patterns over time. Anecdote: imagine an e-commerce company wants to understand customer behavior leading to cancellations. With event sourcing, they have events like order placed, order shipped, payment failed, customer support contacted, order canceled. By analyzing the sequence of these events, they can pinpoint common patterns before a cancellation and potentially intervene. Easy rebuilding of read models. This is one of the biggest wins. If your business requirements change, leading to a need for a new type of query or a different read model schema, you don't have to migrate your core transactional data. Instead, you discard the old read model, create a new projector, and simply replay all historical events from the event store into the new read model. This makes schema evolution much more flexible on the read side. Robustness and resiliency. Events published after successful command processing act as durable messages. If a read model builder fails, it can simply resume processing events from where it left off, or even rebuild itself entirely, ensuring eventual consistency even in the face of temporary outages. Concurrency management. Event sourcing can simplify concurrency control. Instead of locking mutable data you're appending new events. Conflicts only arise if two commands try to append events that violate a business rule, which can be handled by optimistic concurrency checks. Challenges and considerations. Event versioning, storage requirements. While powerful, the CQRS with event sourcing combination is not without its complexities. Increased complexity and learning curve. This pattern is a significant architectural decision. It introduces new concepts, event store, projectors, event publishers, event versioning, and requires a mind shift for developers initially accustomed to CRUD. The operational complexity of managing an event store and multiple read models is higher. The silver bullet, trap. It's tempting to think this is the solution, but it's crucial to apply it where the benefits truly outweigh this added complexity. Don't use event sourcing if a simple CRUD model suffices. Event versioning. As your system evolves, the structure of your domain events might change. For example, if you add a new field to order-placed event, older events won't have that field. You need a strategy for event versioning, which involves handling different versions of an event during replay to build the current state or update read models. This can add significant complexity. Storage requirements. Event stores can grow very large, very quickly, as every single state change is recorded permanently. While storage is cheap, managing and querying large event streams requires careful planning and tooling. Time travel performance, snapshotting, replaying thousands or millions of events to get the current state of a single entity can be slow. To mitigate this, event sourcing systems often employ snapshotting. Periodically, after a certain number of events, the current state of an entity is saved as a snapshot. When reconstructing, you load the latest snapshot and then replay only the events that occurred after that snapshot. Debugging can be more involved. While time travel debugging is powerful, traditional debugging by inspecting current state in a database doesn't apply directly. You need tools that can visualize event streams and projected states. Deletions. You never truly delete an event. If a user wants their data removed, e.g., GDPR, you might need strategies like soft deletion events or encrypting older events with throwaway keys, as simply deleting events would break the historical integrity. Despite these challenges, the synergy between CQRS and event sourcing is undeniable, especially for complex, high-transaction, or highly auditable systems that benefit from a complete historical record and flexible read models. It fundamentally changes how you design, build, and reason about your application's state, providing a robust foundation for agility and scalability. When and why to apply CQRS. Benefits and trade-offs. We've explored the inner workings of CQRS and its powerful partnership with event sourcing. Now, it's time for a critical, pragmatic discussion. Given its complexity, when should you actually employ CQRS? What are its definitive advantages? And, equally important, what are the significant drawbacks and added costs? This chapter aims to provide a balanced perspective, helping you decide if CQRS truly benefits your project. Identifying ideal scenarios for CQRS adoption. CQRS is not a silver bullet. It's a specialized tool best suited for specific problems. Here are scenarios where CQRS often shines: high-volume writes and reads, divergent scaling needs. Description. Applications where there's a significant disparity in the load between write operations, commands, and read operations, queries, or where both are very high but require different optimization strategies. Examples: e-commerce platforms, many reads on product catalog, fewer but critical writes for orders; financial trading systems, rapid position updates; complex historical analysis; IoT data processing, massive ingestion of sensor data, real-time dashboards. Why CQRS helps: allows independent scaling of the read and write sides. You can allocate resources where they are most needed, optimizing performance and cost. If reads are 100x more frequent than writes, you can deploy more read model instances without over-provisioning your transactional write store. Complex business logic. Description. Systems where the rules governing state changes are intricate, involve multiple steps, or require strong consistency guarantees. Examples: supply chain management, healthcare systems, insurance policy processing. Why CQRS helps. The command side provides a clean, well-defined boundary for encapsulating complex business rules within the domain model, aggregates. Command handlers ensure atomicity and correct application of these rules. By separating reads, the complexity of the write model isn't diluted by reporting concerns. Diverse read requirements / multiple read models. Description: applications that need to present the same underlying data in vastly different ways to different user roles or for different analytical purposes. Examples: a customer support dashboard, an executive summary report, a public-facing product listing, and a data science analytical data set, all pulling from the same core order data. Why CQRS helps: enables the creation of multiple, highly optimized read models, projections, tailored to specific query needs, using the most appropriate data store for each. This avoids performance compromises or complex ORM mappings when trying to query a single, generalized schema. Integration with event sourcing. Description: when you need a complete, immutable audit log of all system changes, the ability to time travel for debugging, or the flexibility to reconstruct past states or new read models from historical data. Why CQRS helps? As discussed in Chapter 7, CQRS and event sourcing are a natural pairing. Events generated by commands become the source of truth for building all read models. Microservices architecture. Description: applications composed of many small, independently deployable services. Why CQRS helps? CQRS, particularly when combined with events, provides a clear communication pattern between services, commands to single service, events published by service. Each microservice can implement its own CQRS pattern, using internals optimized for its specific domain. Events can notify other services of state changes without tight coupling. Detailed exploration of key advantages. When applied in the right context, CQRS can deliver significant benefits. Scalability, the most frequently cited benefit. Separating workloads means read and write components can scale independently. Need more read capacity? Add more read model instances. Need more write throughput? Scale the command processing infrastructure. This leads to more efficient resource utilization. Performance. Write performance. The write model can be optimized for transactional integrity and speed of updates, usually by keeping it highly normalized or by leveraging an event store. Read performance. Read models can be aggressively denormalized and stored in technologies best suited for rapid querying, e.g., search engines for complex text search, document databases for UI display, data warehouses for reporting. This avoids complex joins and on-the-fly calculations. Flexibility and maintainability. Independent evolution. The read side can evolve rapidly with UI or reporting changes without impacting the core business logic on the write side, and vice versa. Adding a new reporting view doesn't require schema changes on the transactional database. Technological freedom. Polyglot persistence enables using the best database technology for each specific read model, unlocking optimizations not possible with a single database type. Clarity of concern. Explicit separation of behaviors, do something versus get something, leads to clearer code and easier debugging. Security allows for more granular security postures. You can apply different authentication and authorization rules to command execution, requires higher privileges versus querying, can be lower privileges. Auditability with event sourcing. A complete, immutable history of all state changes provides full audit trails, essential for compliance and forensics. A frank discussion of the significant disadvantages and added complexity. Despite its power, CQRS is not a free lunch. It introduces a substantial amount of complexity that must be carefully considered. Increased complexity, the elephant in the room, architectural overhead. You're dealing with more components. Commands, command handlers, queries, query handlers, potentially multiple read models, message queues, and projectors. This means more things to build, deploy, monitor, and troubleshoot. Code duplication controlled. While the separation is intentional, you'll have different data models and often different code paths for reads and writes, which can sometimes appear as controlled duplication. Conceptual overhead. requires developers to think in terms of actions and events rather than just data manipulation, which is a significant paradigm shift. Eventual consistency challenges data staleness. This is the biggest hurdle. Read models are likely to be eventually consistent, meaning data might not be immediately up to date. This necessitates careful design of the user experience to manage user expectations, e.g., your order is processing, instead of your order is not found. Debugging async flows. Troubleshooting issues across asynchronous message queues and eventually consistent data stores is significantly harder than debugging a synchronous, single database application. Boilerplate and ceremonial code. Implementing CQRS can lead to a lot of small classes, commands, queries, handlers, and interface definitions. While frameworks and code generation can help, it's still more verbose than a simple CRUD repository. Operational overhead. More moving parts mean more things to monitor: queue lengths, projector health, red model freshness, more logging, and more potential points of failure in a distributed system. Deployment strategies become more complex. Higher learning curve. New team members will face a steeper learning curve to understand the architecture, the flow of data, and the nuances of eventual consistency. Training and documentation become even more critical. Initial development slowdown. While it can speed up development in the long run for complex systems, the initial setup and adoption phase of CQRS often involves a slower pace as the team adjusts to the new patterns and builds out the necessary infrastructure. The crucial, it's not a silver bullet warning. This cannot be stressed enough. CQRS is a powerful solution to a specific set of problems, not a universal panacea for all software challenges. Don't use CQRS if a simpler CRUD application suffices. For projects where reads and writes conform well to a single data model, where traffic is moderate, or where immediate consistency is strictly required across the board, and that consistency must be delivered quickly, the added complexity of CQRS will only create unnecessary overhead. Don't apply CQRS for coolness factor. Implementing CQRS just because it's a modern pattern can be a costly mistake, leading to over-engineered solutions that consume more resources than they save. Start small and incrementally. For existing systems, don't try to rewrite everything at once. Identify a specific bounded context or pain point that clearly benefits from CQRS and apply it there first. Learn from that experience before broader adoption. Ultimately, the decision to use CQRS should be driven by a clear understanding of your application's specific requirements, current and future scale, and the team's capabilities. It's a strategic architectural choice that offers profound advantages in the right circumstances, but demands careful consideration of its inherent complexities. Advanced concepts and related patterns. By now, you have a solid understanding of CQRS itself, the rationale behind its existence, and its core components. We've also touched upon its symbiotic relationship with event sourcing. However, production-grade CQRS systems, especially in distributed environments, often necessitate a deeper dive into several related patterns and architectural considerations. This chapter explores some of these advanced concepts that complement and enhance a robust CQRS implementation. Sagas and process managers, handling long-running, distributed business processes. In complex business domains, operations often span multiple steps, involve interactions with different services or bounded contexts, and can take a significant amount of time to complete. If any step fails, the entire process might need to be rolled back or compensated. This is where sagas, also known as process managers, come into play. A saga is a sequence of local transactions where each transaction updates data within a single service or aggregate boundary and publishes a domain event. The saga then reacts to these events to trigger the next step in the process or to implement compensating actions if a step fails. Why are sagas important in CQRS? Distributed transactions. Traditional distributed transactions, like two-phase commit, are often avoided in modern microservices architectures due to their complexity, performance overhead, and tight coupling. Sagas offer an alternative for achieving eventual consistency across multiple services without requiring a single transactional coordinator. Long-running processes. Operations like order fulfillment, which might involve inventory, payment, shipping, and customer notification services, can take minutes or hours. A saga tracks the progress and orchestrates the steps. Compensating actions. If one step fails, e.g., payment fails, the saga can trigger compensating transactions in previously completed steps, e.g., releasing reserved inventory, canceling the order. How sagas work, simplified. A command initiates a saga, e.g., place order command. The command handler processes the command, updates its aggregate, and publishes an event, e.g., order placed event. The saga, which is a separate, dedicated component or service, subscribes to this event. Upon receiving the event, the saga determines the next logical step and dispatches a command to another service, e.g., reserve inventory command. That service processes the command, publishes its own event, e.g., inventory reserved event. The saga receives this new event and dispatches another command, e.g., process payment command. This sequence continues until the overall business process is complete or a failure occurs, triggering compensating actions. Sagas are often implemented using state machines, where each event transitions the saga to a new state and dictates the subsequent action. They are complex to implement correctly as they require careful handling of idempotency, retries, and error conditions. But they are essential for achieving robust workflows in distributed CQRS systems. Messaging and asynchronous communication. The vital role of message queues and event buses in a CQRS ecosystem. You've already seen how message queues are fundamental for updating read models, asynchronous event propagation. Their role extends far beyond that, becoming the backbone of communication in any CQRS and event sourcing system, especially in a distributed context. Decoupling. Message brokers like RabbitMQ, Kafka, Azure Service Bus, AWS SQS SNS allow components to communicate without direct dependencies. A service publishes a message, a command, or an event, and other services can subscribe to it without knowing who published it or how it was processed. Reliability. Message queues provide guarantees for message delivery, at least once, sometimes exactly once, and persistence, ensuring that messages are not lost even if consumers are down. This is crucial for transactional integrity, as events must be processed to keep read models consistent. Scalability. Message brokers are designed for high throughput and can buffer messages during peak loads, allowing consumers to process them at their own pace. They enable asynchronous, non-blocking communication, which improves system responsiveness. Event-driven architecture, EDA. CQRS naturally fits within an event-driven architecture, where events are first-class citizens. The right side generates events, and these events become the primary mechanism for interaction and propagation across the system, enabling other services or read model builders to react to changes. Types of messages, commands. While some commands might be synchronous API calls, in a distributed CQRS system, many commands are sent asynchronously via message queues, especially for non-urgent tasks. Events. Events are almost always published asynchronously via message queues. They communicate what has happened and form the basis for updating read models and coordinating sagas. The selection of a message broker depends on factors like throughput, latency, reliability requirements, and ecosystem integration. Kafka, for instance, is often preferred for high-throughput stream processing and its durable log nature, making it ideal for event sourcing replays. Bounded contexts and aggregates revisited. How DDD structures provide natural boundaries for CQRS. We briefly introduced bounded contexts and aggregates from domain-driven design, DDD, in Chapter 1. It's worth revisiting their importance now, as they provide the ideal structural foundation for applying CQRS effectively. Bounded contexts as CQRS boundaries. A bounded context encapsulates a specific part of the domain, with its own ubiquitous language, domain model, and team. This makes it a natural candidate for applying CQRS. Each bounded context can have its own command and query responsibilities, its own write model, and its own set of read models. This aligns perfectly with a microservices approach, where each microservice might represent a bounded context, internally implementing CQRS. Example: an order management bounded context would handle commands like place order, cancel order, and publish events like order placed. An inventory management bounded context would handle reserve inventory commands and publish inventory reserved events. Aggregates as command consistency boundaries. Within a bounded context, the aggregate is the atom of transactional consistency for commands. A command handler typically loads one and only one aggregate, performs the business logic by calling methods on that aggregate, and then persists changes. The aggregate ensures that all business rules relevant to its internal state are enforced within its boundary. This allows the command side to focus on managing consistency for a small, well-defined piece of the domain, often making the consistency problem much more manageable. Example: an add-to-cart command would operate on a shopping cart aggregate. A process payment command would operate on an order aggregate. By leveraging bounded contexts and aggregates, you naturally align your architectural structure, where to apply CQRS with your business domain, leading to more cohesive and manageable systems. Testing strategies for CQRS and event source systems. Testing a CQRS and event sourcing system is different from testing a traditional CRUD application due to its asynchronous nature and separated concerns. Command validation tests. Unit tests for validating input data within the command itself, e.g., ensuring an email address format is correct. Command handler tests. Unit tests focus on the logic within the command handler. They should verify that given a certain command and initial state, mocked or injected, the handler correctly manipulates the aggregate, and if using event sourcing, emits the correct domain events. They should not touch a real database. Integration tests. These are more involved. You might use an in-memory database or a test container for the event store. The test would send a command, verify the event is persisted, and potentially observe the state of the right model after the command. Domain logic tests, aggregates, critical unit tests for the business rules encapsulated within your aggregate roots. These tests verify that the aggregate correctly applies business logic and emits the appropriate events when its methods are called, independent of the command handler. Query handler tests, unit tests, verify the query handler correctly formats queries and processes results, mocking the read model data source. Integration tests, fire up the read model data store, e.g., an in-memory document database or test container, and populate it with known data. Then, send a query and assert that the correct data is retrieved. Read model projection tests. These are crucial. You need to verify that given a sequence of domain events, your read model projectors correctly update the read model to the expected state. This often involves spinning up the event store and the read model database. Test containers are useful here. Publishing a sequence of events. Querying the read model to assert its state is consistent with the events. Testing scenarios for event versioning and complex projections. Saga tests. Testing sagas, process managers, can be complex because of their long-running, asynchronous nature. You typically test each step, verifying that an event triggers the correct command, and that the saga transitions correctly between states for various success and failure scenarios. This often involves specialized testing frameworks or event simulation tools. End-to-end tests. Despite the complexity, these are vital to ensure the entire flow from UI to command, event propagation, read model updates, and UI display works as expected, especially given eventual consistency. These tests often involve waiting for eventual consistency to be achieved before asserting the final state. The landscape of CQRS and event sourcing is rich with complementary patterns that address the complexities of building highly scalable, resilient, and maintainable distributed systems. While these concepts add layers of architectural nuance, they empower teams to tackle challenges that would be insurmountable with simpler, more traditional approaches. Armed with this knowledge, you're better prepared for the practicalities of implementation, which we will explore in the next chapter. Pragmatic implementation, strategies, and pitfalls. By now, you understand the why and what of CQRS, its relationship with event sourcing, and the surrounding ecosystem of related patterns. assuming you've concluded that CQRS is indeed the right fit for your specific challenges. The next crucial step is to approach its implementation pragmatically. This chapter focuses on how to actually adopt CQRS in a real-world project, offering advice on starting small, avoiding common mistakes, and considering deployment within various architectural styles. Starting small, applying CQRS incrementally to specific problem areas or bounded contexts. One of the biggest mistakes teams make is attempting to implement CQRS comprehensively across an entire sprawling legacy application or a brand new project from day zero. This Big Bang approach often leads to overwhelming complexity, frustration, and eventual abandonment. A far more pragmatic and recommended strategy is to adopt CQRS incrementally. Identify a problem area. Don't start with CQRS for all your entities. Look for a specific part of your application that exhibits the symptoms CQRS is designed to address. A module with high write contention and conflicting read performance requirements. A complex domain where business logic is hard to manage in a single model. A feature that requires significant auditability or historical replay. A specific reporting need that clogs up your main transactional database. A new feature or microservice where the benefits of CQRS are immediately apparent and you have the greenfield opportunity. Example: for an e-commerce platform, instead of refactoring the entire system, pick the order processing or product catalog domain as your first CQRS candidate. Apply to a single bounded context. If you're leveraging domain-driven design, identify a clear bounded context. This provides a natural boundary for applying CQRS without impacting other parts of the system. The context boundary minimizes the surface area of change. Implement gradually. Start with minimal separation. You don't need distinct physical databases for reads and writes initially. You can start with a single database, but use separate object models and access layers for commands and queries. Even this logical separation can bring clarity. Introduce messaging first. As you become comfortable, introduce a message queue for events. Start by just publishing events from your command side, even if nothing immediately consumes them, to get the infrastructure in place. Build the first read model. Then implement your first read model, or projection, that subscribes to those events. Choose a simple, low-risk read model to get the process working end-to-end. Iterate and expand. Once you've successfully implemented CQRS for one module context, then consider applying it to other areas or further optimizing the existing implementation. This incremental approach reduces risk, allows your team to learn and adapt, and provides tangible benefits much faster, building confidence along the way. Common mistakes and anti-patterns to avoid. As with any powerful pattern, there are many ways to misuse or misapply CQRS. Overuse and premature optimization. Mistake: implementing CQRS everywhere, even for simple CRUD operations where it offers no clear advantage. Why it's bad. Introduces unnecessary complexity, development overhead, and a steep learning curve for trivial problems. Avoidance: always ask, what problem is CQRS solving here precisely? If you can't articulate a clear benefit related to scalability, performance, complex domains, or specific read models, stick to a simpler approach. Simpler is always better until proven otherwise. Ignoring eventual consistency. Mistake: building a CQRS system but demanding immediate consistency for all reads, or failing to design the UI/UX around eventual consistency. Why it's bad: you'll end up fighting the architecture. Trying to achieve immediate consistency in a distributed CQRS system almost always leads to complex, fragile workarounds or performance bottlenecks. Avoidance: embrace eventual consistency. Educate your product owners and users. Design UIs that queue operations, provide clear feedback, and acknowledge potential delays, e.g., your order is being processed, not order 123 is not found. Putting business logic in command handlers. Mistake: writing all your domain-specific rules directly within the handle method of your command handler. Why it's bad: violates fundamental domain-driven design principles. Your domain model aggregates becomes an anemic data structure, and business rules are scattered or duplicated across command handlers. This makes the domain hard to understand, test, and maintain. Avoidance. Command handlers orchestrate. Business logic and invariants belong firmly within your domain model's aggregates. The handler should load the aggregate, call a method on it, e.g., order place, and then persist the aggregate's new state events. CRUDing your commands and queries. Mistake. Creating generic commands like create user command, update user command, delete user command, and queries like get user by id query, get all users query. Why it's bad. Misses the point of intent-revealing commands. Update user command gives no business context. Is it updating an address, a password, or a role? Avoidance. Commands should reflect business operations. Register user command, change user shipping address command, deactivate user command. Queries can be more generic, get user profile query, but should still be specific to the data they retrieve, not just raw database tables. Building an event store from scratch. Mistake. Developing your own custom event store solution instead of using a well-established product or framework. Why it's bad. Event stores are complex. Handling durability, concurrency, subscriptions, snapshots, and event versioning robustly is a monumental task. Avoidance. Use proven solutions. Event Store DB, Kafka with specific patterns, or cloud-managed event services are designed for this. Focus on your business domain, not infrastructure plumbing. Neglecting monitoring and operational readiness. Mistake. Deploying a CQRS system without robust logging, tracing, and monitoring capabilities for every component, especially message queues and read model builders. Why it's bad. Debugging issues in a distributed and asynchronous CQRS system without proper observability is incredibly difficult, akin to flying blind. Avoidance. Invest in monitoring from day one. Implement distributed tracing, comprehensive logging, and alerting for queue backlogs, projection failures, and data staleness. Deployment considerations. CQRS within a monolith, microservices context, or hybrid approaches. The beauty of CQRS is its flexibility to be applied at different architectural scales. CQRS within a monolith, logical separation. Approach. All components, commands, queries, write model, read models reside within a single application codebase and are deployed as one unit. The separation is purely logical and code-based. Pros. Simplest to start, no distributed systems overhead initially, can share the same database with different schema tables for read-write, easier debugging. Cons. Limits independent scaling. You still scale the entire monolith. Less technological freedom for read models, tightly coupled deployment. When to use. Early stages of adoption, smaller teams, or when you only need logical separation to improve code organization and clarity within a complex domain, without immediate full-scale distributed benefits. CQRS in a microservices context. Approach. Each microservice implements its own CQRS pattern, handling its own commands and queries for its specific bounded context. Communication is primarily via asynchronous events through a message broker. Pros. Maximizes independent scaling and deployment, allows polyglot persistence at a service level, clear ownership, strong bounded context alignment. Cons. Introduces full distributed systems complexity, network latency, message delivery, distributed transactions, sagas, observability. When to use. Large, complex systems that need high scalability, technological diversity, and independent team deployment. Hybrid approaches. Approach. A common pattern is to have a core transactional monolith, or a few larger services, using a traditional persistence model, but extract specific read concerns into separate, dedicated read-only microservices or data pipelines. These services might subscribe to database change feeds or expose simple queries. Pros. Provide some benefits of a separate read side, performance, scalability for specific reads, without refactoring the entire write-side application. Cons. Still tightly coupled to the main database schema for read model generation, can become complex if not well-defined. Monitoring and troubleshooting distributed CQRS systems. Effective monitoring is paramount for CQRS systems, especially when they become distributed. Metric collection, command throughput latency. How many commands are processed per second? What's the average processing time? Query throughput latency. What's the response time for various queries on different read models? Queue lengths monitor message queue backlogs. Long queues indicate bottlenecks in processing or projection. Read model freshness. For critical read models, how old is the data? This requires tracking the last processed event or the lag behind the right model. Distributed tracing. Tools like OpenTelemetry, Jaeger, or Zipkin are essential to trace the flow of a single request, e.g., a command across multiple services, message queues, and read model updates. This helps pinpoint where delays or failures occur. Structured logging. Log events with context, correlation IDS, command IDS, user IDS, so you can reconstruct the sequence of events leading to an issue. Alerting. Set up alerts for critical issues. Queue backlogs exceeding thresholds, projection failures or errors, excessive latency on command or query endpoints, data staleness exceeding acceptable limits for specific read models. Replay tools. If using event sourcing, have tools for replaying events to troubleshoot projection issues or rebuild corrupted read models. Implementing CQRS is a journey, not a destination. It requires an investment in architectural thinking, developer education, and robust operational practices. By approaching it pragmatically, understanding its trade-offs, and avoiding common pitfalls, you can harness its power to build truly resilient, scalable, and adaptable systems. The next chapter will bring this to life with real-world scenarios and inspiring examples. Real-world case studies and inspirations. The theoretical principles of CQRS and event sourcing gain true clarity when viewed through the lens of concrete applications. While specific company implementations are often proprietary, we can draw from common industry challenges and patterns to illustrate how CQRS provides elegant solutions. This chapter presents abstracted scenarios and a hypothetical design walkthrough, aiming to inspire and ground the concepts in practical contexts. Abstracted examples of CQRS in action. Let's explore how CQRS principles are applied across various industries. One e-commerce platform, optimizing for search and order processing. The challenge: a growing online retailer faced several bottlenecks. Their main transactional database, designed for ACID compliance and efficient order processing, struggled under the load of millions of product searches and complex filtering requests. Generating product listings, category pages, and special promotions involved cumbersome joins and slow queries. The CQRS solution: right side. The core order processing, inventory management, and customer account administration remained on a robust relational database, e.g., PostgreSQL. Commands like place order, adjust inventory, register customer ensured strong consistency. Read side separations, product catalog search, product updates, commands, triggered events, product price updated, product description changed. These events were consumed by a projector that populated a search engine like Elasticsearch or Apache Solr. This red model was optimized for full-text search, faceted navigation, and quick filtering, supporting millions of queries per day with sub-second latency. Customer order history dashboard. Order placed and order updated events were projected into a denormalized document database, e.g., MongoDB. This red model stored customer history as single, easy-to-read documents, perfectly shaped for display on a user's My Orders page. Sales reporting analytics. Events were also streamed to a data warehouse, e.g., Snowflake, for complex by queries and long-term historical analysis, allowing analysts to run arbitrary reports without impacting operational systems. Benefits: dramatically improved search performance, faster customer-facing pages, relieved pressure on the transactional database, and enabled rich analytics. New reporting needs could be met by creating new projections without altering the core system. 2. Financial trading system, auditability and real-time position management. The challenge: a financial institution needed a system for processing high-frequency trades. Beyond speed, paramount concerns included absolute auditability, every transaction, every state change, immediate consistency for trader positions, and diverse reporting requirements, e.g., end-of-day reports, real-time risk analysis. The CQRS plus event sourcing solution. Right side, event sourced. Every trade order, execution, and settlement instruction was captured as an immutable domain event, order placed event, trade executed event, settlement confirmed event. These events were written to a high-performance event store, e.g., Event Store DB. The event store became the single source of truth, providing a perfect, auditable ledger of all financial activities. Commands, place order, execute trade were processed, generating these events. Read side, multiple projections, real-time trader positions. Events were projected into a fast in-memory database or a low-latency NoSQL store, e.g., Redis. This read model maintained the current aggregated position for each trader and instrument, enabling near real-time updates and low-latency queries for trader dashboards. Historical trade analysis. All events were also streamed to a specialized time series database or a data warehouse for quantitative analysts to perform historical backtesting, risk modeling, and regulatory reporting. Audit compliance views. Events were streamed to a separate, highly auditable database for compliance teams, allowing them to reconstruct any transaction and its full lineage. Benefits: unparalleled audit trails, provable data integrity, high-performance write throughput, flexible reporting, and the ability to rebuild any view of the financial data simply by replaying events. The system could survive failures and reconstruct its state accurately. 3. IoT data processing, massive ingestion, and diverse visualization. The challenge: a smart city initiative needed to collect vast amounts of sensor data, temperature, traffic, air quality, from thousands of devices. The data ingestion rate was enormous, but different city departments needed to visualize and analyze the data in very different ways, e.g., real-time dashboards, historical trend analysis, predictive models. The CQRS solution. Right side. Sensor readings were transformed into commands, record temperature reading, record traffic flow, and sent to an ingestion service. This service primarily published these as raw events to a high-throughput event stream platform, e.g., Apache Kafka. This allowed the system to handle immense write volumes. Read side, specialized projections, real-time dashboards. Events were consumed by projectors that updated time series databases, e.g., InfluxDB, or in-memory data grids. These read models were optimized for rapidly serving dashboard queries showing current conditions and recent trends. Historical analysis data science. All raw events from Kafka were archived to a data lake, e.g., S3 or Hadoop DFS, for long-term storage and batch processing by data scientists using tools like Spark or Pandas for complex, ad hoc queries and machine learning model training. Alerting monitoring. Specific events triggered rules that updated low-latency key-value stores for immediate anomaly detection and alerting. Benefits: handled massive data ingestion rates, provided highly optimized read paths for very different use cases, preserved all raw data for future analysis, and enabled real-time operational insights. A hypothetical walkthrough of designing a system with CQRS, a booking platform. Let's imagine designing a simplified booking platform for services, e.g., haircut appointments, fitness classes. Initial problem analysis. Users need to book services, right? Users need to view available slots, read often very high traffic. Service providers, stylists, trainers need to view their schedules, read. System needs to manage availability and prevent double bookings, right consistency. Providers want reports on bookings, cancellations, revenue, read, aggregate. Why CQRS is a good fit, divergent scale. Booking right is critical but relatively lower volume than availability checking read. Conflicting requirements. Availability needs denormalized, fast lookups. Booking needs transactional integrity for concurrency. CQRS design breakdown. Bounded context identification. Scheduling manages all slots, bookings, availability. User management, registration, profiles. Provider management, provider profiles, services offered. For simplicity, let's focus on scheduling. Commands right side scheduling BC. Book service slot command contains userid, servicid, start date time, end date time providerid. Cancel booking command contains bookingid userid. Create service slot command creates a new available slot for a provider. Block service slot command blocks a slot, e.g., provider vacation. Command handlers, right-side scheduling BC, book service slot command handler. Loads the service slot aggregate, checking its state. Available, booked, blocked. If available, marks it as pending and generates service booking initiated event. Saves the service slot aggregate and persists the event to the event store. Crucially, enforces business rule. If service slot is already booked or blocked, it throws an exception, preventing double booking. Cancel booking command handler loads the booking aggregate, marks booking as canceled, generates service booking canceled event, saves booking and emits event. Write model storage, preferably an event store for the service slot and booking aggregates. This ensures total auditability and allows for rebuilding read models easily. Each service slot would be an aggregate stream of events, e.g., slot created event, slot booked event, slot canceled event. Queries read side scheduling BC, get available service slots query. For a given service-id, provider-id, date range. Get user bookings query for a given user-id. Get provider schedule query for a given provider-id, date range. Get booking details query for a single booking id. Read models, projections, and query handlers. Read model 1, available slots view for get available service slots. Technology could be a denormalized table in a SQL DB or a collection in a document DB. Projection. A projector subscribes to service slot created event adds to available slots view, service booking initiated event, removes from available slots view, service booking canceled event adds back to available slots view, service slot blocked event, removes. This view would contain only slotted, provider-id, start date time, and date time, making it highly optimized for searching available times. Read Model 2, user booking history for get user bookings. Technology. Document DB or denormalized SQL table. Projection. Subscribes to service booking initiated event, service booking canceled event, service booking confirmed event, if payment happens later, etc. Stores booking id, service name, provider name, date time, status, tailored for user display. Read Model 3, provider schedule for get provider schedule. Technology. Optimized for quick time-based lookups, potentially another document DB collection. Projection. Subscribes to relevant events to build a chronological schedule of all bookings blocks for each provider. Messaging. A message broker, e.g., Kafka, is used to transport events from the right side to the various read model projectors. Lessons learned and insights from implementations. Complexity is real, but manageable. The initial setup and development time are higher, but once foundational pieces are in place, adding new features or scaling becomes more straightforward. Event design matters. Well-designed, granular, and immutable domain events are the key to flexible read models and robust event sourcing. Badly designed events can lead to tightly coupled projections or make rebuilding difficult. Observability is non-negotiable. Without robust logging, distributed tracing, and monitoring, troubleshooting an asynchronous, distributed CQRS system becomes nearly impossible. Team buy-in is critical. The philosophical shift requires everyone on the team, developers, architects, and even product owners, to understand and embrace the concepts, especially eventual consistency. Start simple, logical CQRS first. Even just separating models within a single database can bring significant clarity and flexibility before fully adopting polyglot persistence or event sourcing. These examples and the design walkthrough demonstrate how CQRS, especially when paired with event sourcing, provides architectural flexibility for challenging domain problems. It allows systems to scale effectively, offer robust auditing, and adapt to evolving business requirements by optimizing each part of the data flow for its specific purpose. The key is to be judicious in its application and rigorous in its implementation. The future of system design with CQRS. We've journeyed through the intricacies of Command Query Responsibility Segregation, from its foundational principles to its powerful synergy with event sourcing, through its practical applications and the wisdom of its pragmatic adoption. As we conclude, it's worth reflecting on where CQRS positions itself within the ever-evolving landscape of software architecture, and to offer some final thoughts for those embarking on this architectural path. How CQRS integrates with emerging architectural trends. The architectural landscape is dynamic, constantly shaped by new technologies, increasing demands for scalability and the pursuit of agility. CQRS, far from being a niche or outdated pattern, is surprisingly well aligned with many of the most prominent emerging trends. Serverless architectures. Serverless functions, like AWS Lambda, Azure Functions, Google Cloud Functions, are inherently stateless and react to events. This makes them a natural fit for CQRS. Command functions. A serverless function can act as a command handler, triggered by an API gateway request or a message in a queue, processing a command, and then emitting events. Event publishers, consumers. Serverless functions can easily push events to event buses, e.g., AWS Event Bridge, Azure Event Grid, or consume events from message queues to update read models. Read model generation. Functions can be used as projectors, triggered by new events, to update read models hosted in serverless databases, e.g., DynamoDB, Cosmos DB. The paper execution model of serverless works well with the often bursty nature of commands and event processing. Event-driven architectures, EDA. CQRS, especially with event sourcing, is fundamentally an event-driven pattern. Events are the primary mechanism for communicating state changes, triggering reactions, and building derived views. This makes CQRS a cornerstone of sophisticated EDAs, fostering loose coupling and allowing services to react asynchronously to business facts. The move towards domain event-driven services is a profound shift that CQRS supports completely. Distributed ledgers and blockchain-inspired systems. While primarily used in specific contexts, the core concept of an immutable, verifiable, and append-only log of transactions, similar to an event store, resonates strongly with the principles of event sourcing. If systems require an absolute, cryptographically secure history of all state changes, the ideas behind event sourcing and the command-driven nature of state changes align well with distributed ledger technologies. Data mesh and data products. As organizations strive to decentralize data ownership and treat data as products, CQRS provides a powerful framework. The right side provides the authoritative domain truth, while various read models, data products, can be developed by different teams, tailored for specific data consumers, analysts, other services, applications, and governed independently. The event stream acts as the conduit for these data products to stay aligned with the source. Reactive systems. Reactive systems prioritize responsiveness, resilience, elasticity, and message-driven communication. CQRS, with its emphasis on asynchronous event processing, independent scaling of components, and clear separation of responsibilities, aligns perfectly with the principles of reactive system design, enabling applications to be highly responsive and resilient under varying loads. Reflections on CQRS as an enduring pattern for modern complexity. CQRS emerged from a need to manage complexity in enterprise applications, driven largely by the insights of domain-driven design. It addresses a fundamental tension: the conflict between optimizing for state change and optimizing for state retrieval. As systems continue to grow in scale, distributed nature, and the diversity of their data consumption requirements, this tension only intensifies. CQRS provides a powerful, opinionated way to explicitly resolve this tension. It forces architects and developers to think deeply about intent, consequences, and data flow. It's a pattern that, once adopted, fundamentally changes how teams reason about their systems. It's about clarity, making explicit the difference between doing and knowing. Flexibility, allowing different parts of your system to evolve and scale independently. Optimization, leveraging the best tools and techniques for specific read and write concerns. Resilience, building systems that can be eventually consistent and handle failures gracefully. CQRS is not merely a transient fad. Its core principles are timeless within the context of complex, transactional systems. The tools and technologies we use to implement it will continue to evolve. But the underlying drive for separating command and query responsibilities will remain relevant as long as applications deal with competing needs for consistent state changes and efficient data access. Final advice for aspiring architects and developers navigating complex systems. For those of you looking to apply CQRS or grappling with architectural decisions in complex systems, here are a few parting pieces of advice. Understand the problem before the solution. Before leaping to CQRS, thoroughly diagnose your system's pain points. Is it genuinely suffering from conflicting read-write requirements, or is it a simpler problem that could be fixed with indexing, better queries, or a simpler caching strategy? CQRS is a powerful solution to a specific problem. Start with domain-driven design, DDD. Many of CQRS benefits are amplified when built upon a strong DDD foundation, bounded contexts, aggregates, ubiquitous language. DDD helps structure your problem space in a way that naturally aligns with how CQRS segments responsibilities. Embrace incremental adoption. Unless you're on a true greenfield project with a deeply experienced team, don't try to go all in from day one. Pick a single, well-defined problem area or bounded context. Get it working, learn from it, and expand gradually. Your team's learning curve will be your greatest asset or biggest hurdle. Prioritize observability. In distributed, asynchronous systems, traditional debugging becomes difficult. Invest heavily in logging, distributed tracing, and comprehensive monitoring across all components: command processing, event queues, read model projections, read models themselves. You need to see the entire flow to diagnose issues effectively. Manage expectations, especially around eventual consistency. Be transparent with stakeholders, product owners, and end users about the implications of eventual consistency. Design your user experience to account for potential data lag, providing informative feedback rather than frustrating inconsistencies. Simpler is better until proven otherwise. The beauty of software architecture lies in its infinite possibilities, but the wisdom comes from choosing the simplest path that effectively solves the current and anticipated problems. Resist the urge to over-engineer. Keep learning. The world of software architecture is always evolving. Stay curious, read, experiment, and engage with the broader community. The patterns and principles discussed in this book are robust, but their application will always benefit from fresh perspectives and continuous learning. Building complex systems is a challenging but immensely rewarding endeavor. CQRS is not a magic wand, but it is a potent tool in the architect's arsenal, enabling the creation of systems that are not only powerful and scalable, but also agile enough to adapt to the relentless pace of digital transformation. May your architectural journeys be insightful, efficient, and ultimately lead to robust, delightful software solutions.